Now that we've looked at some simple traversals of sparse tensors using a loop nest, we're going to look at a couple of examples of more complicated sparse tensor computations. In particular, we're going to look at the convolutional layer. This was the full convolutional layer of a typical deep neural network, representing multiple filters, one for each output channel, and each filter has multiple input channels. We do the convolution channel-wise against the input activations to generate the outputs. We're of course going to look at a simpler case for our code. So we're going to look at a one-dimensional, again, reduced down to a one-dimensional convolution, reviewing the uncompressed representation. So this is the code for an output stationary uncompressed 1D convolution. So because it's output stationary, we traverse in the outermost for loop the indices of the output. In the next for loop, we do the indices of the weights, and we notice that both the indices Q and S correspond to the coordinates of the desired elements in the tensor. We then need to compute the position or coordinate in the third tensor, W, and then we can use those, even though those are nominally coordinates, we can use those because in an uncompressed, we can use those directly because in an uncompressed representation, the coordinate and the position are the same. So we simply use the coordinate in the input activation tensor in the coordinate of the filter weight in the filter weight tensor and the coordinate of the output for the output. Okay, if we're going to look at how this operation proceeds, what we're essentially doing is looking at a window of inputs, and we start with the first weight, the first input. We use that to create a partial sum in the output. We then move to the next filter weight, next input, contribute more to the partial sum in the output, look again at the last weight and the last element of the window in the input activations, and we complete the sum. We then slide the window over and work on the first weight, the first input activation in the window, and start a partial sum, then move to the next, and so on. Now, if the weights are sparse, we'd like to be able to take advantage of the fact that some of the weights are 0, and we'd like to not spend time or computation energy on those 0 weights, because we know that a multiplication by 0 is going to be a 0 result, and adding 0 to something doesn't change its value. And so here I've given an example of a set of weights where the middle weight is 0, and what we're going to assume is that we have some kind of compressed representation. I've just drawn a fiber tree which could correspond to a compressed representation, and so now we know that we're talking about coordinate 0, which has value 8, and coordinate 2, which has value 6, and those are the weights. So my computation is going to rely on these fiber coordinates and their values, and I still have a window of input activations that I care about, and I can work on the first weight being at coordinate 0 and work on the corresponding spot in the window. But then when I go to the next computation, I now, based on the fact that I'm working on coordinate 2, I don't need to look at relative coordinate 1 in the input activations. I can jump to the end of the window, coordinate 2 in the input activations, and I have now completed my partial sum. when I slide my window, I'm going to do the same thing. I work on the first weight, the first corresponding input activation in the window. I jump to the next input activation corresponding to coordinate 2 of the weights, and finish another sum. So let's see what this does to our loop nest representation of the computation, or correspondingly the architecture we need. This was just a repeat of the code for the uncompressed output stationary data flow. And the conversion is now that we basically changed the data type of f from being an array to being a tensor. And the next thing we see is that when we traverse the filter weights, we use the traversal over the fiber in the top and only rank of the filter weights, and return correspondingly the coordinate and the filter weight. The first thing we notice is that that this is a concordant traversal of the filter weights, which we saw from the example before. We looked at each weight in order in the filter weight tensor or vector because it was one-dimensional. The other thing that we do is we still do our computation of the coordinate of the corresponding coordinate of the input activation we want to work on, and then our computation is going to contribute to a partial sum at the appropriate output, where again, because the output is still uncompressed, position and coordinate are the same. Again, we also need to be able to access an input activation, and again, if the input activations are an uncompressed array, the position and coordinate are the same, and so we can access it directly by position, but we multiply it by the value that we accessed during this concordant traversal of the filter weights. If we want to look at this in an animation of the activity in the filter in the fiber tree, what we see is that we traverse each weight in order and just keep on going back over the weights, and we jump around in this sliding window in the input activations. So we look at one and then the next, because we know that there is no coordinate 1, so we jump back and then jump over 2. And if we look at the outputs, this was output stationary, so we simply contribute and have activity in one output activation until it's done, and we move on to the next. If we want to look at a more space-time representation of that same activity, what we see looking at the tensor weights, the activity is going to be look at the coordinate 0, coordinate 2, coordinate 0, coordinate 2. So again, these are the coordinates of the different weights, and this is time moving across. So we touch coordinate 0, coordinate 2, coordinate 0, coordinate 2. If we look at the input activations, if we think about there being a window in these coordinates, in the window we look at 0 and 2, and then 0 and 2, 0 and 2, 0 and 2. And in the output activations, we see that we contribute to the same coordinate for a couple cycles, basically computing partial sums from the two different weights and corresponding input activations. Then we move on to the next two, the next two. Now, as we saw before, given that loop nest representation of the mapping of our tensor computation, we can create a representation of what the hardware would need to be in order to support that computational flow, that schedule in both space and time. And so what we see here is a representation of the compressed or compressed weights of the filter weights of the problem, and that's going to be indexed by a position. We're going to step through all of the positions repeatedly, generating filter weights. We get the coordinate, which we combine with the coordinate that we're going to be working on for the partial sums. So we're going to step through the partial sums here and calculate, and that partial sum is going to come out and is going to be added to repeatedly. Given the coordinates of both the filter and the output, I can calculate the coordinate of the input that I want. Because this is an uncompressed representation, I take in the coordinate, I generate a payload, which is the input activation I want. I do my multiply, accumulate, contributing, and I have some control lines here indicating when you have finished a partial sum and move on to the next one. So that would correspond to the hardware, and the time loop model is going to be able to infer, what is the activity in all of this hardware for that data flow, and because it has been given a specification of the architecture, the hardware architecture, it will actually be able to determine whether the hardware could even be configured into that format. Now, just like we saw in the uncompressed data flows mappings, we saw that we could reverse the order of the loops. And if in our sparse weight situation, if we reverse the order of the weights, we end up with a weight stationary data flow instead of output stationary, and yet the representation can still be interpreted in the loop nest. And again, we see that we're going to end up with concordant traversal of the filter weights. And we can map that into the hardware, where now our position generator is generating a sequence of positions for the filter weights. Those filter weights are now held in a latch because it was weight stationary. We still do computations of the appropriate output. We still input the coordinates into the uncompressed partial sums and the coordinates into the uncompressed input activations, because coordinates and positions are all equivalent for uncompressed representations, and do our multiply, accumulate, contributing to the outputs. Obviously, these cases were quite simple. If we want to extend this modeling to the other dimensions of the DNN, what we're going to end up doing is adding loop nests for 2D input activations and 2D filters. We're going to have multiple input channels, multiple output channels, and we're going to want to add parallelism. Well, how did we add parallelism in the uncompressed case? Well, what we did was we effectively tiled the computation. And tiling in an uncompressed representation is very easy. You just have to know where to make your references in that uncompressed data. It's a little bit more complicated for sparse data, but conceptually actually very similar. So what we're going to do is look at, okay, how do I tile or split a fiber tree containing fiber tree tensor? So I've started here where I have a tensor with a sparse tensor. So you can see that there's non-contiguous coordinates here and their values for each of the coordinates. And what I want to do is I want to split this so that the occupancy of each tile is the same. And so I'm going to split it equally into 2 elements per tile. And so the way we're going to do that is we're going to change our tensor from a rank 1 tensor with only one level in the tree, one fiber, into one with multiple ranks and multiple levels in the tree. And we say, okay, let's first grab the first two coordinates of our original tensor. I grab them, I assign that coordinate 0, and then I create a new fiber in the next rank, which is going to be the first two coordinates in the original. So I'm going to have 0 and 2. Notice I've named these ranks after the name of the original rank, and I've called them W0 and W1, just to indicate that I have two separate ranks. I then grab the next two elements. I call that coordinate 1 in the top rank, and I grab 3 and 5. So I'm grabbing coordinates 3 and 5 from the original, putting them into the second rank, and then I'm going to grab the next two coordinates and final two coordinates of the original tensor and declare that's coordinate 2 and put a fiber in the next rank with the last two coordinates. So now what I have is I have a new fiber tree, and we can imagine whatever representation would be appropriate. We're going to pick a representation that is efficient for the implementation that we want. But in the abstraction, I just have a two-level fiber tree that I can traverse as we saw before. So if I want to show a loop nest representation for a computation where I employ a splitting of my tensor, I can show something like this. So this is a parallel weight stationary data flow with sparse weights. And what are we going to do? We're going to first split the weight fiber equally into groups of 2. And so I basically get groups of 2 weights, which is what this method on the fiber tree does. There would be a corresponding activity that we would need to do on whatever concrete representation of the tensor that was selected. And what do we get out of this? When we traverse this, what we get is a coordinate, which is the top level coordinate, which is just going to be consecutive numbers, and a reference to a fiber which has the split portion. I'm then going to traverse I'm actually doing a splitting of the output so I can get parallelism in the output, but because that was uncompressed, that's easy. I just say I'm going only over 1/4 of the outputs, and I do them in groups of 1/4. I then have a parallel 4, so I'm running in parallel all the coordinates that were in this split, and so I actually am going to work on 2 weights in parallel. In my next step, I'm going to work on 4 outputs at once, and I need to calculate the proper coordinates for each output, and also the coordinate of the input activation. In this case, I've still left them uncompressed. It gets more complicated when you have compressed tensors for more than one of the operands in the operation. Okay. And finally, I have to look up the input activation. Again, put coordinate equals position, so that was easy. And I accumulate multiple outputs each spatially. If we actually extended this design by adding more loops for input and output channels, what you actually get is the Cambricon, something very, very akin to the Cambricon X design, where they picked particular representations for each of the tensors. If we want to look at that activity in animation, what we see here is these filter weights. We don't see any green here because I ran a case with only 2 filter weights, but now we have both of the PEs, the two highlighted colors, the yellow and the light blue, are both active. And what are they going to do? They're going to work on each pair of input activations at the appropriate place in the window. And this window is going to slide across. And what we see was we had even more parallelism because we were working on 2 weights at once. And so the 2 PEs are actually both contributing to this partial sum, which would be like designed as a spatial sum in the hardware. Okay, in the this is basically the end of the first part of the background presentation. You can get more information on this part of the presentation with a shameless plug for the book that we wrote, and there is a large section in this book that describes sparse computations in the form that was presented here. And now we're going to go on to the second part where we're going to go into a more deeper dive on the processing and modeling of sparse computations. Nellie will take over.